let's have a look at the parametrics of our conics. So, well, we don't see a lot of the circle, but for the sake of completeness, it is one of the conics. So let's have a look at this parametric. There's a point xy. For the circle, we actually define it in terms of the angle that it makes at the center. So I can draw up that triangle. The x value, well, a bit of trig, x over a would be cosine theta. So x would be a cos theta. And the y value, we get a sine theta. So they're the parametric coordinates. Remember, a is a constant, it's just whatever the radius is. So theta is the parameter. So a cos theta, a sine theta. And if you don't believe me, watch this neat little proof. X squared plus y squared would be a squared cos squared plus a squared sine squared. But cos squared plus sine squared is 1, therefore it equals a squared, and that is what we recognise to be the equation of a circle. More interested in the ellipse. So how do we define it? Again, it has to do with that angle at the centre. But what we do is we draw in, there it is, the auxiliary circle. X squared plus y squared is a squared. So the actual angle, theta, is not the angle that P makes with the centre. There's where we draw the triangle. Okay? So from P, you draw the vertical, you go up to the auxiliary circle, and the angle that makes with the centre is the angle theta. Okay? Now, to work out the x and the y coordinate then, well, x, we certainly know the x value because it's just going to be the same as the auxiliary circle. So x, once again, becomes a cos theta. The y value, if I was to draw the circle with the smaller radius, where it cuts, or the hypotenuse cuts the smaller circle, it actually is straight across from the point P. And so I can use the y value using the smaller circle. So we'll get y over b is sine theta, b sine theta. So very similar to the circle, but the difference being that we don't have a common radius. So the x has the major one, so a cos theta, the y has the minor one, b sine theta. And again, I can prove that by substituting into x squared on a squared plus y squared on b squared, and we can show, yep, that does equal 1. All right, all the things we were interested in when we did parabolas. We want to find equations of tangents, of normals, and things like that. So let's derive those. There's an ellipse. So x squared on a squared becomes 2x on a squared, y squared on b squared, 2y b squared dy dx. Remember, implicit differentiation, chain rule, rates of change, call it whatever you like. So rearranging all that, we get that the derivative is minus b squared x on a squared y. So if I'm talking about, and I'm using Cartesian coordinates to start off with, just x1, y1, then the derivative is minus b squared x1 on a squared y1. That'll be the slope of the tangent. So subbing that in, something beautiful happens. Got to manipulate it a bit. So I've expanded out, got rid of the fraction, and then I've rewritten it in a strange sort of way. I mean, with lines we normally put it in the general form, or y equals mx plus b, but here what I've done is I've put the variables all on one side and anything that's constant on the right hand side. Remember, x1 and y1 is constant because that's the random point. Now the reason I've done that, I can divide everything now by a squared b squared and have a look at what we get. x1x on a squared plus y1y on b squared is x1 squared on a squared plus y1 squared on b squared. But the right hand side, I know what that's equal to, because that point lies on the ellipse. So therefore it must satisfy the equation of the ellipse. So it equals 1. Now have a look at that equation and think about the equation of the ellipse. It's essentially the same thing. Because the ellipse was x squared on a squared plus y squared on b squared. Here I've got x1 times x. Well, if you just pretend the 1's not there, x times x, x squared. and y1y, or pretend the 1's not there, what y times y. So it looks like the equation of the ellipse itself. Makes it very easy to remember. Let's have a look at the normal then. Now the slope of that will be the negative inverse. So we get a squared y1 on b squared x1. Let's expand that all out, and once again I've done the same thing. I've moved everything that has a variable in it to the left hand side. If it's just got constants, it's on the right hand side. This time I'm not going to divide by a squared b squared. This time I'm going to divide by x1 y1, because that becomes easier to remember. A squared minus b squared. An ellipse, what's the significance of that? Remember that formula? E squared is equal to a squared minus b squared over a squared. Well, if I multiply both sides by a squared, I get that a squared minus b squared is a squared e squared. The foci squared. So I could rewrite that one to be, well, the left-hand side, but equals a squared e squared. Now, how do you remember the left-hand side? Well, we're dealing with a normal rather than a tangent, so we're thinking of inverses. We don't inverse the x and the y, but we inverse the a squared and the x1, the b squared and the y1, and then we change the sign, because negative inverse when you're talking about perpendiculars. A little bit harder to remember, but there is a pattern there that we can go with. Well, what if we use parametric coordinates instead? Well, let's sub that into the derivative that we found before. And we have b cos theta on a sine theta. It's very tempting to turn that into, well, cos on sine would be cotan, wouldn't it? Yeah. But don't do it. Avoid the temptation. And this is why. When we sub it into the tangent formula, if I now multiply everything by a sine theta to get rid of the fraction, then on the right-hand side, we get sine squared plus cos squared, which is, of course, 1. Now, had I changed that to cotan, I wouldn't have got that immediately. So the right-hand side becomes just AB, but if I divide by the AB, I can then make it equal to 1, just like the other one, and there's our equation. Of course, the other way you could have done it is you could have remembered the tangent formula in Cartesian form and just substitute in a cos theta for x1, b sine theta for y1. I mean, and then you would get that equation as well. I guess it depends what information you already have when you're doing the question. What happens with the normal? So now it's a sine on b cos. Expand that one out. This time I'm going to divide everything by sine theta cos theta. And that'll leave me with the a squared minus b squared on the right hand side, like I had before with the Cartesian one. And so there it is, ax on cos theta minus by on sine theta is a squared minus b squared, or of course it could be a squared e squared, depending on how you prefer to write that one. Let's just sort of summarise all that. There's our tangent. It looks like the actual ellipse itself in Cartesian form. The normal, well, the right-hand side becomes the focus squared, if you like. And on the left-hand side, we've inverted the x1s and a squareds and so on and changed it to negative. And in parametric form, we get x cos theta on a, y sine theta on b equals 1. But as I say, you could just substitute the parametric coordinates into the Cartesian form and you'd get that. And on the right-hand side, remember, there is no extension 2 reference sheet. So they won't give you these. Sometimes they might in the question itself, but be very careful what the question actually says. If it says, show that, then okay, you've got to work it out or do something like that, show that it works. But sometimes they use the phrase, write down. In that case, you can just quote it. Oh, well, I know this is the formula, I'll write it down. The number of marks a question worth as well is a bit of a guide. You know, if it's worth 1 mark, well, they're hardly going to expect you to derive the whole thing and do all that. So it is, in a lot of cases, unless they're specifically asking you to find the equation of the tangent, it's certainly fine to just quote it And so remembering that it takes on the form of the ellipse itself can be a useful thing. Because we go, oh, well, yep, that would be the equation for this one. So if I had to find the equation of the tangent at this particular point, 2 minus root 3 on 2. And let's pretend I can't remember the formula. We'll do it from scratch. So I'll differentiate, and we get minus x on 16y. And so at the point 2 minus 3 on 2, substitute in. My derivative is 1 on 4 root 3. Point slope formula. Oh, looks a bit ugly like that. Let's multiply everything by 4 root 3. I've put it in general form, so x minus 4 root 3y minus 8 is equal to 0. I suppose I could have done it. If I remember, I could say, oh, well, I know the equation of the tangent will be x1 on 16 plus y1 is equal to 1. Remember, it mimics the equation itself, and then just substitute in 2 minus root 3 on 2 to x1, y1. And that would work. Find the equation of the normal. Now it's in parametric form. And again, I'm going to derive it from scratch. We're going to have to differentiate some trig. So remember, we've just done that. So differentiate sine, we get cosine. The other thing we're going to differentiate, of course, is cosine. That goes to minus sine. So remember that. So x is 2 cos theta. Dx to theta is minus 2 sine theta. Y is sine theta. To y to theta is cos theta. So using chain rule, rates of change, whatever, we get our derivative is cos theta or minus 2 sine theta. I find that easier than trying to rewrite the equation in terms of y and x. So differentiate it, because we're just dealing with parameters. Yes, my slope's in terms of theta, which is the parameter. Now we want at pi on 6, so sub in pi on 6, I get minus root 3 on 2. We want the negative inverse of that for the slope, so 2 on root 3, and it just becomes a standard, find the equation of a line question now. And there it is. So 4x minus 2 root 3, y minus 3 root 3. Here's a more interesting question. They've told me y equals mx plus k is a tangent to the ellipse. I know it is a tangent. So we have to prove this relationship. A squared m squared plus b squared is k squared. I think I've seen a couple of different ways of doing this. Which way did I do it this time? Let's see. I've gone right back to scratch where I've said, oh, well, x is a cos theta. So again, I'm going to derive the slope here. So I get y dx is minus b cos theta on a sine theta. Now, I know that y equals mx plus k is a tangent. So therefore, the derivative would equal m, slope of the tangent. So I now have this relationship. The slope is minus b cos theta on a sine theta. Just going to play around with that. And I get am sine theta plus b cos theta is equal to 0. The other thing we know is the tangent meets the ellipse at that point of a cos theta, b sine theta. That's the point of intersection. Therefore, it must also satisfy the equation of the line. Because not only is it on the ellipse, it's on the line as well. So I get b sine theta is am cos theta plus k. Rearranging that, I have am cos theta minus b sine theta is equal to minus k. I've got two equations. I've got two variables. One is theta, the other is m. Everything else there, the constants as far as I'm concerned. So I'm going to eliminate the one I don't want, that being m. I'm going to do it a curious way. I'm going to square the first equation. A squared m squared sine squared plus 2abm sine theta cos theta plus b squared cos squared is equal to 0. I'm then going to square the second equation. A squared m squared cos squared minus 2abm sine theta cos theta plus b squared sine squared is k squared. Well, if I add the two together, the 2abm sine theta cos theta and the minus 2abm sine theta cos theta cancels. I get an a squared m squared sine squared plus cos squared, that's 1. I get a b squared sine squared plus cos squared, that's 1. So I have my relationship, a squared m squared plus b squared is k squared. So that's one way you could do it. I suppose another way we could do it is we could use the discriminant idea. We know if we were to solve these things simultaneously, the discriminant would equal 0. You could try that. That should work as well. The chord of contact. Remember, chord of contact. So you have an external point. You draw in two tangents. And where they meet the ellipse, join that up. That becomes a chord, and we call that the chord of contact. So we now know that the tangent there at P would be x1x on a squared plus y1y on b squared is equal to 1. Now if I draw in a second tangent, which touches at, let's call it Q, point x2, y2, that one would have the equation x2x on a squared plus y2y on b squared is equal to 1. Now T lies on both lines. Therefore, it satisfies both equations. So therefore, it's true to say x1 x naught on a squared plus y1 y naught on b squared is equal to 1. It is also true to say x2 x naught on a squared plus y2 y naught on b squared is equal to 1. Well, we have our equation then. Let's look at it closer. We've just said there's the equation of the blue line. There's the equation of the green line, but I've substituted in the x naught and the y naught. PQ must lie on that line. Remember, the equation of a line is simply some constant times x plus some constant times y plus some constant number. That's all we're looking for. Well, that's what we've got if you look at it. Right? X naught on a squared. If I substitute x1 into that, I'll get x naught x1 on a squared. If I substitute y1 to that, well, hang on, that's the blue line. We already know that to be true. If I substitute x2, y2 in that, I get the green line. Well, we know that to be true. Feels like I haven't done anything, but there it is. But the beautiful thing about it is, again, look at the pattern. The equation of the chord of contact is the same as the equation of the tangent, is the same as the equation of the ellipse itself. Now, it's not a coincidence. Because imagine we got the point T and drew it closer and closer to the ellipse itself. What's going to happen to those two tangents? They're going to get closer and closer to each other till the point, if you like, that limiting point where T actually now touches the ellipse itself. Well, those two tangents now become one tangent. So the chord of contact is the equation of the tangent. We get the same thing. All right. That's what we shall play with today. So some out of Patel, some out of Cambridge.